Alright, so this is a continuation from last lecture. Here's the theorem we were working on at the end of class, plus a little bit more. First of all, what's our assumption? We're assuming we have a vector space V, finite dimensional, with subspaces W1, W2 through Wk. The claim then, and such that the sum of the subspaces is all of V, which simply means you take a vector from W1 all the way through a vector from Wk, add them together, and anything in V can be obtained in such a way. This notation alone does not suppose these things, though. Alright? So, the following are equivalent. In particular, this mapping pi from the Cartesian product of the subspaces to V, defined by the Cartesian product of this k tuple is the sum of the components, is an isomorphism. So, I could think of one in words as saying V is isomorphic to the Cartesian product of the subspaces. Condition 2 is often referred to as independence of the subspaces. In other words, the intersection of one subspace with the sum of the remaining subspace is just 0. 3, uniqueness of representation is usually what I call 3, which means that for every x in the vector space, you can find unique x1 through xk such that you build x back as the sum, right? 4, if beta is a basis, beta I is a basis for wi, then if you string the bases together for the subspaces, you get a basis for the whole space. And finally, thanks to King at the end for pointing this out, if there exist vectors which add to 0, then each of the vectors has to be 0, is another equivalent condition. Alright, so let's get to it. It shouldn't take too long to prove the rest of this. It would take me 30 minutes of class to write this out, though. So, last time we already proved 1 implies 2 and 2 implies 3. So next move, assume 3 is true. In other words, assume for each x and v there exists unique vectors in each subspace, x1 through xk, such that x is equal to that. Alright? Now, our goal is to show that if we string the bases together, we get a basis for the whole space. So we need some notation here. And I should really... Uh-oh. Maybe I need some candy. So if we let beta I be this basis, I'm inventing some notation for each of the bases, so vi1, vi2, vid1. So where the dimension of wi is di, alright? Then I can consider the union of all these, which is just stringing them together. So 1, 1 to I d1, 2, 1 to 2 d2, k1 to k dk. Alright, that would be the concatenation of the basis beta 1 through beta k. And then my goal is to show that that's a linearly independent spanning set for the whole space, right? So first of all, I note that if I take a linear combination of these guys equal to 0, then if you look at it, what I've got is this is in W1, this piece is in W2, this piece is in WK, right? But on the flip side of things, we can write 0 as 0 plus 0 plus plus 0, right? So, by uniqueness of representation, right, that gives us that, sorry. By uniqueness of representation, that gives us that each one of these sub-combinations, these linear combinations, must separately be 0, since there's a unique way to represent 0 as a sum of k vectors, right? But then, by linear independence of the basis beta 1 and beta 2 and so forth and beta k for the subspaces, which we're assuming, right? We assume that beta I was a basis for wi. Then we get that all these coefficients are 0, so we get the totality of all the coefficients are 0, which says that beta is a linearly independent set. And then finally spanning follows pretty easily, because if I have x is equal to a sum of these vectors, right, where each one of these is from from W1 through WK, then because the beta 1 is a spanning set, I can build x1 from the v1i's all the way out to xk I can build from the vki part of basis beta. But in total, that's an element of the span of beta. So therefore beta is a linearly independent spanning set for V, which proves that it's a basis, which establishes 4. Alright, by the way, this proof is very reminiscent of the homework problem I gave you guys to prove that, the linear independence implies equating coefficients. To me, this feels very, very similar to that. But anyway, just a comment. 3, Assume 4, that is, assume that the union of the basis is a basis for V, given that each beta I is a basis for Wi. Suppose our goal is to show that 5 is true, right, which is the unique representation of 0. So suppose you've got a sum of vectors which gives you 0, right? Then since each of the vectors is in the subspace Wi, and that's the span of beta I, then there have to, we can use the notation like I did last time, and we can expand each xi in the basis, and then we can set that, so this is just, the sum which gives you x1 plus the sum which gives you x2 plus the plus the sum which gives you xk. I can rewrite all of that as one grand glorious total sum over the Vij's, which, all of these together give you the basis beta. And but the basis is a basis, so it's linearly independent, which implies that the coefficients are 0. And once all the coefficients are 0, that implies the coefficients for each x sub I is 0. So x1 is 0, x2 is 0, xk is 0, consequently 5 holds. So all that remains then to prove is that 5 implies 1. If we can prove 5 implies 1, then we'll have the equivalence of 1, 2, 3, 4, and 5. So we assume 5 holds true, that is that there's a unique decomposition of 0. If x1 plus x2 plus plus xk is equal to 0, then x1 is 0, all the way out to xk must be 0. So we seek to show that pi, defined as such, is an isomorphism of the Cartesian product in V. We already noted in our last lecture that pi is clearly a linear transformation, so all we need to show then, to show it's an isomorphism, is that it's a surjection and an injection. So to see that it's a surjection, that's just a simple calculation. If I pick a vector in V which is given to us to be the sum of these subspaces, that means that I can pick an x1 in here, an x2 in here, an xk in there, such that V is equal to the sum of x1 plus x2 plus plus xk. And then common sense and a moment of just intuition will give you that if I map the tuple x1, x2, xk, I get x1 plus x2 plus xk by definition of pi, which is V again. V being arbitrary, we've shown that pi is a surjection. It remains to show that the kernel is 0. If we could show the kernel is 0, that would show that it's injective and hence an isomorphism. So suppose that we've got something maps to 0. In other words, suppose that this tuple x1 through xk is mapping to 0. In other words, this is in the kernel. Well, if this is equal to 0, then by 5, which we're assuming, we've got that each one of these is separately 0. But that means that the kernel of pi is just the 0 vector, which means that pi is an injection, which means that pi is an isomorphism. And consequently, we've shown that 1 implies 2, implies 3, implies 4, implies 5, implies 1, which logically will give you 1 equivalent to 2, 2 equivalent to 3, 3 equivalent to 4, 4 equivalent to 5. So there you go. These are our 5 equivalent characterizations of a vector space being formed by the direct sum decomposition of W1 through Wk. And just the takeaway message from this is when this is the case, we write the following. We write V is equal to W1 plus circle W2 plus circle plus circle Wk. And what we'll do today is to study what happens when we look at linear transformations which respect this structure in a special way. We'll find out it's very beautiful. But anyway, thanks guys.